So Log9, it's a company that started from IT Roorkee, 2015. So it's been a while. It's the 9th year that we're on. The company is established. One of the focus areas that we work is to ensure that we can make products that are designed in India and for the tropical world, because that's where the same temperature and pressure conditions are there. Economical status is also similar. Mission is driven by technology, and then the purpose is very straightforward, that every product has to lead to something better in the world. Let me see if I can play this video. This is a cell line that we have set up. This is where we make our lithium-ion cells. So we make two kind of chemistries here. One is the LTO, which is lithium titanium oxide, and that kind of allows you to do things much faster. That LTO allows us to build packs that can charge in minutes rather than in hours. So probably Log9 makes the world's fastest charging batteries. Two-wheelers that are getting charged in 10 minutes, three-wheelers getting charged in 30 minutes, four-wheelers that are getting charged in about 45 minutes, something like that. And then the LFP that we do. Most of the work that we do is on cylindrical form factors, but we do prismatic cells. We also do make a lot of LFP now. So that's the entire journey. We don't touch raw materials. We're not into the mines, but anything that comes out of mine, then we get started onto it. So all the way from making the cathode and the anode material, forming it, then coating it onto the electrodes, and then going ahead doing the entire design. And then not just stopping at the cell, but have the 250 megawatt hour battery production center in Bangalore. So that allows us to make larger form factor, more scaled up batteries. Then we send it to the OEM integrates it, and then we come back into the business again, where we take these vehicles and then we lease it in the market for all your Amazon, Flipkart deliveries. That's happening on most of those, we carry Log9 batteries in it, so it's a downstream business for that. The innovation node is kind of this, everything is sitting on the cell side, so complete form factor control on the cell design, and then complete control of the battery pack design. So that's what we tried to achieve over the last couple of years. These are the two outcomes that have come out of this entire 9 years of work. The LTO packs, we call it the Rapidex, and they're typically 9 times faster than anything that's there out there. LFP, on the other hand, is competing on price with the Chinese imported chemistries. So they're at least about 2.5 times more faster than the current imported Chinese products. I'll give you one flavor of what we do. There's a lot about that we do, but I think one of the most important things that we've been doing recently is digital twinning. How do you make your battery a digital twin? Then you can control it, understand it, you can monitor its state of health in the market. You can run your BMS algorithms to see whether the cells are performing. You can predict SOH and SOC much more accurately. So the way Log9 does it is, we take a real cell, and the idea is to make it into a kind of physics-based cell. So a lot of simulation goes into that. That's a whole simulation engine. There's an entire team of scientists that work onto this. And the outcome is that once you have the cell, you have all the parameters of the cell digitized. Then there are some AI/ML algorithms that we've developed, which allows, so when you get a bunch of cells together, there will be slight difference in their capacity. Each cell is slightly different than the other. And it's a nightmare to pack them all together and make a battery pack. It's because it's the cell-to-cell variability that leads to a battery pack is functioning. Yeah. So it's cell-to-cell variability that kind of, a lot of people say, think of a mobile phone, it used to work really well, and then one day it drops dead. That's a monolayer cell. And then you have in a battery pack, maybe you can have hundreds and thousands of cells. And how do you make those cells behave across a temperature, discharge profile, and a drive cycle to behave similarly? What we do is, there's multi-variable algorithms that kick in. They understand a cell, and when you digitize it, you understand everything. You understand, the voltage curves, the internal resistance, the ACR, the DCIR. So all the parameters are kind of figured out initially. And then a bunch of cells are collected and they're converted into some kind of a buckets that allow these similar cells to be paired together. Now the cell-to-cell variability is reduced. Log9 packs actually carry cell-to-cell variability to the point of 0.3%. As a comparison, your Tata Nexon carries 3%, so they're 10x higher in the cell variability than Log9. Once those buckets are kept together, there's a particular pack that's designed, so this particular goes through a manufacturing step. It's designed for a particular vehicle, so it's been designed for its BMS and its controller that works optimally with that vehicle. So an architecture comes out, which is you start with the physical cell and all the way till the battery gets integrated into the vehicle. It's digitized. Now, the batteries also come enabled with telematics and all the other parameters because you've got sensors, you've got devices, you're reading everything on the cell and you're pumping that data back using your telematics. And then you're correcting the thermal profile, the charge discharge profile. So that allows you to now digitize even the battery. So what happens is that now what was digitized is a cell when you're manufacturing it. Once it gets started to use in the market, it gets digitized as a battery. So I think by now we've done over 6,500 battery packs in the market. All the battery packs, they talk back to my mobile phone every day. And I can control it, I can see it, I can do a state of health, I can do preemptive maintenance if we need to intervene into the battery somehow. So this is a digital token set where this gets done. To monitor all of that, you need a layer of embedded engineering. So we've developed the entire BMS at Log9. So it's not just one BMS, it's something similar to multiple hardware electronics coming together under one chipset design. So the EVC, the telematics, the slave BMS, even the VC is all clubbed into one chip. And that's the brain. So there's absolutely no more electronics in the battery other than this one piece. And that reduces the circuitry, the design, the cost. And this BMS can allow, so for example, when we're trying to charge an LTO pack, we're pushing 200 amps of current. So when you want to charge, for example, my mobile phone takes about 40 minutes to charge. A battery pack size of this desk will take about 10 minutes. So you can imagine how much current we're passing through it. So this guy can handle all of that. While you're doing it, it has to maintain and balance so that data voltage don't develop. So all those kind of algorithms are there. Plus this is smartly connected to the entire cloud infrastructure. So all the algorithms, which are your state of health algorithms and SOCs algorithms, they run on cloud. Yeah, so auto calibration, it's photon enabled, all that stuff. We call it Charvik. That's how the company's done, made about $13 million doing this stuff last year. Over 150 patents, about 125 R&D team, and picked up a lot of awards on the way. Those are the product categories in which we're selling our products. So two-wheelers, three-wheelers, forklifts. Now we're also selling stuff to the airport for the things that push the aircraft back and forth. You need high safety, you need fast charge. All of that's been done a lot. Some of the deployments that we did. This is MERS. All the four-wheelers are now being converted to Log9. Large three-wheeler cargos. These are very interesting use cases in India. So we've done a lot of best solutions, sending stationary packs to places where the colder temperature, because LTOs can work across minus 30 degrees. So we made these colder temperature batteries and then shipped it to the Indian Army in Leh Ladakh. So the entire Indo-Tibetan China border, that's where the power demands are there for very advanced batteries. So we're working with them, supplying to them. Also working with ISRO so that they can have these kind of very advanced lithium-ion LTO packs or LTO cells that can operate in those kind of severe temperature conditions. LTO is extremely safe. I can cut it in the middle, no problem. We bake it about 180 degrees, doesn't catch fire. So it's in a controlled environment when your safety concerns are very high, energy density requirements are compromisable. You work with that. But all of this has been designed with LTO and LFP. So a lot of people ask what's so unique about Log9 batteries, and I think it's a mix of many things, because when you have control at all the layers, you control the cells, you control the power electronics, you control the algorithms, you control the temperature, thermals of the battery, and then you digitize that entire asset so that you can maintain the monitor. That's where probably a battery becomes like a token. All Log9 batteries, they come enabled with multiple charging options. So one of the things we wanted to ensure was not depend our battery packs to be dependent on any charging protocols. So GBT, we recently launched Type 6. So two-wheelers, Type 6, you can charge it. We don't believe in swappable batteries, so you can just charge them on a Type 6, 10, 15, 20 minutes, they're good to go. It's easy for me to stand here and speak about what we did in the 9 years, but this is how one of the battery centers, that's how we were doing it from. On the left, what you see, we're building things with hands and packs and just trying to learn what a battery is. From there to reaching to a completely 250 meg automated lines now, which are fired up. Ultimately, all of this is leading to this one North Star that we have. We're almost on our way. So we recently did how many kilometers our batteries have done. They've done about 30 million kilometers. Doesn't sound like a big number, but imagine 30 trips to the moon. That many distance we've done on the batteries. But a lot of our batteries are now entering into stationary storage, so solar, wind, wherever there are, those kind of demands are there. On all of these targets, we're almost 40% done. And target is by 2030, we should be able to clock most of them. Thank you.
Nice lecture, first of all, congrats. You mentioned about 40,000 cycles. How did you do that? Definitely by modeling or individual doing cycling studies?
So we've been cycling for almost 3 years now. We've reached to something like, and we've done expedited 45 degrees tests also. We've got 3 data points with us. We have 1 data point that has taken our cycle life to about 8,000 cycles so far.
Okay.
And the retention of the capacity is a high 90s. So we are well on the way. But the cells are capable to give 40,000. But in the market, the warranties that we give is about 6,000 to 8,000.
No, that particular 40,000 value, how did you arrive at? Is it due to some kind of modeling, studies and extrapolation?
Yeah, correct.
Okay. And second thing is, you mentioned about LTO and LFP. What are the other electrodes? LTO combines with NMC and LFP with graphite?
Yeah, because LTO, you need a high voltage electrode, so it cannot work with NMC, LFP won't work.
Yeah.
So you've got NMC on one side, and then you have the titanate on the other side.
Okay.
NMC is graphite on one side.
Okay. Interesting that you are supplying to defense also. By chance, if they take it to Leh or Siachen, how about the performance at minus 40 degrees? Like what is going to be the electrolyte? Have you looked into that, whether you can perform at minus 40 degrees with the same discharge rate or anything like that?
Yeah, so we've got data because they've been operating it in Ladakh. In fact, Sonam Banshu, the guy on with the 3-idiot movie was made. He took a couple of our batteries, he's running it in Ladakh. It's a year. So we got data up till minus 25. Seems to be working.
25 is okay, minus 25 is okay. I don't know, I have not visited your website recently. If it's okay, then you can just publish this data. Like it works at even minus 25.
Minus 10 and minus 25 degree temperature data will be published. We're planning to publish this year because the stationary packs are going to go out in the market. We call it the ice charge. The packs are called ice charge. So whatever the real life data that we have, we've done thermal chamber data as minus 10, minus 20. The cells have been certified to operate till minus 60, which is always with some kind of qualification.
Okay.
But I think the real life case is if you can make it work at about minus 20, minus 30, should be okay.
Excellent. Once again, thank you.
So very interesting. the digital passport, the digital cell, twin cell, is it like the digital passport they are trying to introduce? I don't know if you know in the European Union. And the other question is, how far do you go in studying? Because you start from the materials, right?
Yeah.
So how far do you go in the simulations? Do you start with the parameters that have an issue, or this is just a field effect, or what kind of where do you start in the simulations?
Yeah, well, the model got created because we knew exactly what were the raw materials. So there are two kind of models that we built. One is which is a completely physics based, in which we particle size. You build a model, you do a molecular dynamics simulation, you fit all the curves. And then you start to fit real-time data into that, and then you start to curate your dielectric coefficients and everything else. So a lot of equations were driven because we were doing simultaneous discharge charge cycles. And then we were doing failure modes in terms of cathode cracking, and there is a leaching of something, if there is a lithium plating that's happening at fast chargers, so we'll dissect the cells, take them under electron microscope and try and do fundamental work over there, and then fit that back into the equations. So a lot of mathematical almost out of the 150 patents, about 25 patents came from mathematics that we did around this.
So they are published in the patents?
Patents have been published.
Okay, so just going back to your BMS, so I have a specific question. So in a pack you have, say, 1,000 cells.
Yeah.
So is the BMS able to handle, let us say, one cell which is not performing? Let us say, assume it's a hypothetical situation. So will the BMS be able to detect this? That, somewhere in location X, Y, Z, you have a cell non-functioning.
Yeah, absolutely. That was one of the major criteria for which we built the BMS. It was for delta voltage. So when the packs are running, there will be slight delta milliamp voltage, that deviation that will get created. And generally the BMS will not be able to sense it, and you need something more like an active balancer.
Right.
So there is a two combination system that we build with. There's an active balancer that pushes in more current to balance the cells, and because LTOs are very high powered, power cells, not very high cells. But then BMS has this, there are certain ports in the BMS which are sensing ports. So each cell gives certain amount of data which is on the voltage and current that we will drive. But also there are temperature sensors and others. And then there is an active balancer that continuously monitors the delta voltage being developed. So we start to see that if there is a deviation in one of the cells or not. In LTO it's very perfect. In LFP we do struggle sometimes because LFP denaturation is very different than LTO. But at a cell-to-cell level, when it gets to thousands of cells, maybe it will become complicated. But right now, Log9, the cell form factor is 6600 series, so very big cells. So even in a three-wheeler, I only have 88 cells.
Okay, and because you're applying very high currents, so you must be having any novelty in the heat management there.
Yeah, massive. We have rooms in which we have done immersive cooling. They were working with total energy, got their dielectrics, immersed cells completely into that, created the entire electronics around it. So we do three form factors of cooling. Generally in two-wheelers you don't have space to cool batteries.
Yes.
It's generally air-forced.
Right.
And the problem is, like, if you look at the Ola Ether scooters and the ones that we do, everything is kind of packed up in a very small space, so you don't have much conduction over there. In three-wheelers, we have an opportunity, but we've gone ahead and built batteries which are massive, the size of the TV. We cut it in the half, and really big, high voltage platform batteries. So for Indian Railways, Log9 got first company to be empaneled to supply batteries to Vande Bharat. So the form factor started to change a lot. And for that, for the Indian Railway packs, we needed very advanced cooling. So there we have glycol-based plate cooling. Prismatic cells which are sitting flat onto the plates and then being cooled from the plate. For our high power energy systems, we have created cooling through bus bars. So we actually don't cool the cell, we cool the bus bars directly. And also the cells that we've made, they don't use any tabs. These are the first tabless cells, and our patents came out 6 months before Tesla.
Yes.
So because these are tabless cells, so the heat signature is always locked up to the top and the bottom. And hence I can cool it from there rather than trying to cool the entire surface. We've done thermal glues, potting mixtures, the entire test.
Thank you.
What sample of digital twins you are maintaining for the battery?
Sorry?
The digital twins being maintained. What sample of digital twins you are maintaining for each model or all the batteries which are sent out?
Unfortunately, we're so nerdy that each cell goes through a cycling, and so I have a data of how the cell was cycled when we woke it up. And then, so today we maintain 100% data, but our manufacturing is now crumbling to the point where we cannot. So we're now doing some averaging where all cells do not have to be cycled, but we do maintain digital twin of all the battery packs.
Any on-grid deployments, and also what's the battery pack cost? Is it?
It's about 2 times more expensive than anything that's there in India. So these are expensive packs. LTUs are typically 2 times more expensive because of the nature of LTU. LFP, we are about 10-15% more expensive because there's a lot of other components that are built inside it. From a grid scale, we are now starting to enter into it. We made 1 megawatt hour containerized solution complete with cooling and BESS system. So that's being deployed right now with our partner Jupiter. This year we're expecting to deploy at least 4 to 5 megawatt hour stationary packs, and next year probably scale that up.
So, it was a nice question. How do you deal with the waste generation during the battery manufacturing process?
Yeah, massive question. One of the things is when we were doing the cell production line, the 50 megawatt hour line, we wanted to use as less as NMP, as more of an aqueous process, have anodes processed through aqueous processes and all of that stuff. So probably Log9 cell line is one of the greenest cell lines in this part of the world. Energy consumption is about 33% less because we use a lot of aqueous processing in place. Most of it we don't vent out. Most of it, the problem actually is more at the end of the line when you will have some rejections on the cathode materials. The yield on the cell lines are not 100%. What you mix, you don't get the full out of it. So that is something that has been a little challenge. But we personally invested into 2 recycling companies. One is Metastable, I don't know if you know them, and then there's another recycling company, Loha. So we tied up with them. So some of our active rejected material goes to them for recycling. Cell recycling has not started. We've done some part of it. LTOs will live for next 10 years, so we don't have to worry about it. LFPs probably will come back into the market. We warrantize them for about 5 years, but some rejects needs recycling. And for some of the other very, for example, how do you dispose of electrolytes and some of those harmful chemicals? We've tied up with agencies that take care of that, so we don't directly recycle ourselves.
One question about the heat management, which is leading to thermal runaway. Is it an issue today? Why can't phase change between these be employed and
Yeah, there should be. Like I'm always, so you've seen, I've not even touched NMC because I'm super scared to touch NMC. Because I generally see NMCs, and our entry to lithium-ion has been because, just from the past, what I've heard today, we were never a lithium-ion cell company, we were always a fuel cell company. We built India's first aluminum air fuel cell. And when we built that a couple of years back, we needed something to store the energy from the fuel cell. And the first thing we went and bought was these NMC cells, and our labs will catch fire, and literally our tables will catch fire and all of that stuff. So we've had a very bad experience controlling NMC. We've seen them go into thermal runaway, anything that goes above 65 degrees. And then there is this, there's enough energy, there's enough electrolyte, combustive oxygen trapped inside those electrolytes to lead to that. So NMC we don't touch. LFP I'm still okay because NMC, the thermal runaways that we've done, they will go to 150 degrees, they will smoke up, the electrolyte will vent out. The cell designs have those venting points out, but they won't catch fire, so at least there is no injury caused by fire. There is a shutdown through smoke. LTO is safer so that way, but we've not done phase change material, we've done thermal glue. So it's a liquid that you make a mold and then you put the cells into it, the pack around it. It doesn't changes the phase, but it does dissipate the heat out. We've done phase change, but I think we are jumping that hoop and directly going to immersive cooling because that's super massive. I can cool the batteries down by 10 degrees in a matter of about 4 to 5 minutes if I have a small chiller unit in the vehicle. We're also contemplating if we can use the same compressors that is there in the vehicle to get the chilling capabilities back into the batteries. Otherwise, you have to, some of the other companies are doing, you have to cool the chargers and then pass the coolant into the batteries when you're charging. So our opinion is the phase change is a little tricky, but immersive, more expensive, but the specific heat opportunity that is there in that is much higher. So, and potting mixtures work. I mean, we have data on cylindrical cells at climb 15 degrees, and then if you put them into a potting mix, they only climb 5 degrees. And India being at, Delhi will operate at 45 degrees. So your tolerance to go to 60 is just 15 degrees, and you will get there very easily. All our batteries are going to 60 degrees easily.
One general question. Bach is actually talking about price of $50 per kilowatt hour at the cell level.
Yeah.
How long we need to go to match that price? I am not exactly asking your price, just I'm putting a general way.
I was looking at rupees data 104 kilowatt hour for a LFP and let's say about 76 kilowatt hour. Sorry.
$76 per kilowatt hour.
So we're looking at about 30% difference between let's say lithium-ion and sodium-ion. That was the discussion. But yes, you're right. If you would have asked me a year back, I would have never even thought that we will get LFP cells from China at a price point of $50 per kilowatt hour. But it is the reality. We are getting our cells landed in India in the order of $60. So the question to the room now is, and to Prabir, if the LFP is available in the market at $50 per kilowatt hour, which I can see, that it will go there. The installed capacity in China is close to about a terawatt. And if this is the, and just by dimension, if this is the amount of lithium-ion that China produces, this is what we buy.
Okay, yeah.
Drop in the ocean. So even when you are such drop in the ocean gives it to you at $50. The moment India scales up to its targets of 2030, and I think the LFP stabilized at $50 to $60 per kilowatt hour. The thing is, we are not seeing the impact of that for us in our EVs. The scooters and cars are still expensive, but the battery manufacturers are getting it at a price point which is dream.
Because I see most of your market is either with the OEM or with this kind of agencies like defense or railways or something like that. That's why I asked this question. Sorry to that.
No, absolutely. The price pressure is there for all of us. But I think at $50, my assumption is there should be no reason why an EV should be more expensive than an ICE engine now. In my mind, the price parity has already happened. It's not happened in the market. But Log9 can produce an EV today which is cheaper than an ICE engine.
So thank you, Mr. Pankaj Sharma, for your insightful presentation on Log9 Materials and high performance storage. So I'd like to call upon Mr. Ravi Kumar to felicitate Mr.
Thank you. Thank you.